Hello everyone, welcome back to Chapter 24, Part 3. I've been having some more issues with static in the background, and I think I got it figured out. It's the power cord that I've had hooked up to my laptop. So what I'm going to have to do with these future videos here, the backup battery for this only lasts for about 45 minutes. So if I start running low on the battery, I'll just have to pause the video, charge it up, and then we'll come back in a little bit. But for all of you that are watching, you shouldn't notice any difference. But I want to do this just so we can improve the sound quality of these videos. And in the last video, we went through a couple of derivations for the electric potential, and we saw the electric potential derivation for a single point charge. We also saw how we could add together the potentials produced by multiple charges in a system. And so now what we want to do is we want to continue with that theme, looking at different distributions of charge and finding what electric potential we will produce in that system. And where we're going to start today is with the electric dipole. And so this is something that we've seen in the previous chapter, specifically chapter 22. And in that case, we derived the electric field that was produced by the dipole. So if we remember, the electric dipole has equal and opposite charges separated by a distance of d. And if we combine the values of the charge magnitude with the displacement vector, we produce the dipole moment. And we used P to represent that. So we can just as easily replace D with the dipole moment P. But today, instead of finding the electric field, we want to find the electric potential. If you recall, when we tried to solve for the electric field, our author had us solve for the field at a point directly above the axes of the dipole. And that was so that we could keep everything in the problem one-dimensional. And that was because electric fields are vectors. Vectors have components. And so we didn't want to venture to other locations in space, because that would mean that we would have to introduce more math, which we could do, but it would just take us a lot longer. And if you remember, there was about 3 pages of algebra that I skipped over in the electric dipole derivation for the electric field. But now we're working with electric potential. And potential is a scalar. So potential does not care about direction. And for a single point charge, the electric potential is kq over r. And that means that we can look for the electric potential anywhere in space that we want. We can look directly above, off to the side somewhere, maybe even the middle. So let's discuss some of those possibilities. No matter what point in space we look at to measure the potential of the system, keep in mind that what we're really doing is looking for the net potential that is produced by all of the charges in the system. So in our case, we have the positive charge of the dipole and the negative charge of the dipole. So let's try the center point of our dipole, because that was actually where our author wanted us to measure things from. Our author wanted us to use the midpoint of the dipole to measure things like the electric field. And so maybe we should try that in this case. But if I were to take our expression for the electric field produced by a single point, well, all that would mean is that we have positive Q over half the distance, d, and then we have to add that to the potential that the negative charge is producing, also a half distance d, and when we put those together, we get a net electric potential of 0. So this is different from what we had for the electric fields, because our charges, our positive charge would produce an electric field that travels away from the positive charge. Our negative charge would produce a negative field that moves towards the negative charge. If we added those fields together, we would not get a 0 field value, yet we are getting a 0 potential value. So do not mistake the behavior of the electric potential as being the same as the electric field. The simple fact that we are no longer working with vectors changes the math. Now, since I have 0 potential at this midpoint here, that would suggest that any point in space that is the same distance from our charges is going to have a 0 potential. And we can accomplish that by drawing a horizontal line in either direction. And any point on that line would be equidistant from the two charges. So each of these charges would be a distance of r from that point. And so now I would put in r instead of d over 2. And I'd still get 0. So everywhere on that blue line, we have an electric potential of 0. If I were to move to a point that was above this line, any point above that line would be closer to the positive charge and further away from the negative charge. And so now we're talking about having to figure out which one of these is going to win the battle of the mathematics. And because the positive charge is closer, the ratio of charge to separation distance for the positive charge is going to come out to be a larger number, and so everything above that blue line is going to end up with positive electric potential, and everything below the line will have negative electric potential. Alright, so, whoops, didn't want to do that. So now that we know that, let's focus on a random point out in space. So this will be our random point out in, well, if I could get it colored here, there. This will be the random point out in space where we want to measure the electric potential. So time to start setting up the math for this problem. Now, down here, the summation expression that we have is actually still valid. All I need to know is how much charge each individual particle has and how far away each particle is from the point in space where I'm trying to measure. So here we have the distance that the positive charge is from our point out in space. Here we have the distance that our negative charge is from the point out in space. And then we're going to attempt what the author did last time, which is to see if we can reduce all of the math such that we measure from the center point of the dipole. So we're going to start right here with the equation that we've set up, and I'm going to clean this up a bit because both of our terms have a lot of things in common. We have the 1 over 4 pi epsilon, and both terms have the same magnitude of charge, so I will bring that out front. But what remains inside the parenthesis just ends up being the difference in the R values for the positive and negative charge. So at this point, we could just measure the distance, R positive, R negative, plug those values in, and then get the net potential for the system. But if you remember our previous discussions on dipoles, these dipoles are going to be pretty small. The reason why it's so important to discuss dipoles is that you run into a lot of electric dipoles in areas like chemistry, and if the if the structure of the dipole is in fact very small, then it just makes more sense and it's more efficient to measure from a general center point of that dipole. And that's where we're going to go with the math. We're going to see if we can rewrite all of this stuff with more general measures like R. Just this R value right here. Okay, here we go. The first thing that we're going to have to do is we're going to have to combine those two terms. And the way we combine any kind of fractions is we have to have a common denominator. When in doubt, multiply the two values together. But that's going to involve a cross multiplication with the numerators. And if we do that, we will get R negative minus R positive in the numerator, and then we'll have R positive, R negative product in the denominator. Okay, next, we're going to make some pretty big assumptions. The first thing that we're going to do is we're going to look at our diagram a bit closer, so I'm going to zoom in on this. I'm going to draw a line between the positive charge and the line R negative. And I'm going to draw it in such a way that the line intercepts at a right angle. And so what this does is it basically takes the length of R positive and sets it equal to this portion of R negative. And the reason we want to do that is so that we can figure out what is this remaining length right here. All right, to do that, as you can see here, we have a right triangle now. We have a right triangle right here. And I want to find this side length here. To do that, it would really help if I knew one of the angles. So maybe we could measure the angle between the direction that our dipole moment points and the direction that we have to travel in order to get from our negative charge up to our point up in space. And so that would be the angle theta. The distance between our two charges is d. And so now we're good. We can actually solve for the length of this portion, or this side of the triangle. That is the side that is adjacent to the angle. And so this side length here, this side length here is d cosine theta. Now, why is that length important? Well, remember that we just said that this portion right here, and things are getting kind of messy, so I'm going to back off on this stuff. Whoops. No, go back. Okay. Let's see, I'll use this color then. So this portion right here, we said that this was the difference in the total length of R negative and the length of R positive. Okay, these two yellow highlighted areas, those are what we were assuming to be the same length. But that yellow highlighted portion, that is not the full length of R negative. We also have to consider the d cosine theta. And so that difference right there is the d cosine theta. And that's going to be useful to us for two reasons. First of all, it brings in the value of the dipole moment itself. In order for the dipole moment, we have to have two things. We need the charge and the separation distance. Well, R negative minus R positive, that's what we have in the numerator of this parenthesis set. So I can rewrite the numerator as d cosine theta and then we can bring d out to the front and combine it with q to make p. So we have p cosine theta 4 pi epsilon naught, and then we still have the 1 over R positive R negative to take care of. But we now are starting to put together an expression that depends on the dipole moment itself, which contains information about the dipole, like the separation distance between the two charges. And that's one of the things that our author wanted us to do. That's one of the things that we needed to incorporate. But then that cosine theta, what's that cosine theta mean? Usually, whenever cosine theta shows up, it means that there's been some kind of angle relationship between vectors. And, well, this is a electric potential, it's a scalar. So why are we seeing cosine show up? and I'll explain that in just a moment. Because before I do that, we want to take care of this R positive, R negative combination. We want to find a substitution for that as well. All right, back to our diagram, and I'll try to clean this up again without doing that exactly. I just wanted to get rid of the highlighted portion. There we go. Get rid of that stuff and that. The stylus does not want to do what I tell it. Okay. Well, I'll just draw it again. Okay. So the last thing that I'd like to do with this diagram is, instead of using R positive, R negative in any of the mathematics, I'd like to take those values and see if I can replace them with just R. Now, we notice that in our expression down in the denominator, we have the product of R positive, R negative. Up in the diagram, if we were to categorize these R values in terms of actual length, R positive is the shortest of all of those lengths. R is sort of in the middle, and R negative is the longest of the two. And we are taking a product of the shortest leg and the longest leg. And so how would that product compare to, say, taking the product of the middle leg times itself? In other words, R is basically the average length of the positive negative lengths. And so if we were to just take the average length of the two, multiply that against itself, well, then we could make the assumption that the product of R positive and R negative is just equal to the squared value of R. And that is the value that is measured from the center of the dipole. And that was the other goal that our author had in mind. So our author wants to take all of that and replace it with R squared. And so now we have a much nicer expression in front of us. We have our dipole moment, P. We have R squared as measured from the center of the dipole. But then we still got that cosine. So let's talk about that cosine. And I'll draw the dipole again right here, just so that we're not constantly shifting back up. Alright, so up here we have our point in space where we want to measure the electric potential. And we do have a vector in our statement. We have the electric dipole vector, which, reminder, always points in the direction of the positive charge of the dipole. But there's a second vector in this expression, which is the vector R, that tells us how we're going to measure from the midpoint of the dipole out to the point in space where we want to measure the potential. And if we put these two vectors together, P and R, well, what's the angle between them? So now I do have to shift back up here, but well, I have theta as being the angle between the dipole moment and R negative, but if the point in space is relatively far away, then the angle measure between our dipole moment and R negative is really no different than the angle measure between our dipole moment and the vector R that we use to measure from the center. And you might ask, well, how valid is that assumption when you say that the point in space has to be far away? Well, far away compared to the separation distance between your charges. And remember, this separation distance is really small. We're talking molecular size versus, who knows, maybe a centimeter away or even a millimeter. That's going to be orders of magnitude larger than the separation distance between the charges. And so this is a relatively safe assumption to say that we're dealing with the same theta value. And so with those two vectors, using cosine theta as the measure between those two vectors, well, we've seen that plenty of times in the past already. Whenever we have the combination of two vectors and a cosine relationship, that is almost exclusively a dot product. And the way that we evaluate the dot product is that we take the magnitude of each and we measure the angle relationship between the two. And the result of a dot product is a scalar, which is exactly what we want. Our net electric potential has to be a scalar. Okay, so I've got the electric dipole, I've got the cosine theta, but where's the R value? And some of you might say, well, it's right there, except it's in the wrong place. I need the R value up in the numerator somewhere so that I can combine everything and call it a dot product, but I don't have an R value up there. So what do? Well, we get a little inventive with the math. So we've got P, we've got cosine, we've got the R squared. I need to figure out a way to sneak in an R value in the numerator. And you might say, well, just put the R in the numerator and then put another R down in the denominator so that you multiply by 1. And that sounds like a good idea. But that means that we would have, let's see, we would have PR cosine theta over R cubed. And then we could reduce that down to P dot R over R cubed. Okay. And there's nothing wrong with that, but we can do better in the math. You'll notice that I wrote R with a vector hat because that's the direction that we're headed here. We have to have R as a vector because R is pointing in a certain direction. I need that information for the cosine relationship. But R is also carrying a magnitude with it. R is carrying the length value. And that magnitude of R is eventually going to cancel with one of the R values down in the denominator. And so the fact that you multiplied by 1 to accomplish this, and then we had to turn that into a vector Well, this is a very special type of vector that shows up from time to time in a number of classes. We effectively just have the number 1, but it carries a vector notation. And this is what we call the unit vector. It's a vector of magnitude 1, but it carries the necessary directional information for that vector. So here's what we're going to do. We're going to allow the magnitudes of those R values to reduce so that we're back to having an R squared in the denominator. But now I need the unit vector for R to stay in the numerator. And the way we'll do that is we put a little caret over the top, and this tells us that we have a unit vector. So that R value is understood to be a unit vector. And now watch the magic of mathematics as it unfolds. We have the P vector, the dipole vector, that we have to dot with the unit vector. When we evaluate any dot product, we take the magnitude of each vector times the cosine of the angle between them. The magnitude of the dipole moment is P. The magnitude of a unit vector is 1. And so what do we get in the end? We get exactly what we had before, but now it's in a form that can be written as a dot product. And the reason I stress this is the importance of being able to measure theta between those two vectors. But feel free to reduce this down to the P cosine theta. As long as you know what your theta value is for measuring, then you can do that. Great thing about this is that this expression will work anywhere in space. We don't have to limit ourselves to being directly above the dipole moment. We could be, if we want to. What would we get if we were a distance r directly above the dipole moment? Well, in this case, we would have our two vectors running parallel to each other. That means that the cosine relationship between r and p is 0 degrees. Cosine of 0 is 1. And so we would have p over 4 pi epsilon r squared. And that's it. That is the electric potential, a distance of r directly above the dipole moment. If we were to drop below the dipole, a distance of r. Okay, well now we're no longer at 0 degrees for the cosine relationship. We are at 180 degrees for the cosine relationship. Cosine 180 produces a -1, and so we get a negative potential, which is exactly what we should expect, because we already argued the fact that if we're above the midpoint of the dipole, we should be getting positive potential. If we're below the midpoint, we should be getting negative potential. And so, well, let's try a point on that line and see what happens. We're going to use our new expression to measure the electric potential out at that location. Now our dipole moment has always been pointing up. That's not going to change. But the R value that we need to measure from the midpoint of the dipole out to the point in space where we're trying to measure is now at a 90-degree angle with respect to P. So cosine of 90 degrees. Cosine of 90 is 0. In other words, we have 0 electric potential everywhere on this line. And so our equation is matching up perfectly with every possible situation that we could think of. And so now you can start measuring the electric potential at any other point in space. You just have to have an angle measure between the direction of your dipole moment and the direction that any of your R vectors point. Okay, so that brings us to the end of the electric dipole. I am going to see if I can pause the video, but I'm not seeing the icon that's going to let me pause this. And so, well, it looks like I've got a fairly good amount of battery here, so I'll keep going. But if you want to pause the video, feel free to take a break. Next thing we're going to take a look at. Now we need to start looking at larger distributions of charge in our system. And the first distribution of charge that we looked at with respect to electric fields was the line of charge. And we did this one first because it was the worst of all the derivations. And so I guess we'll try this one first just to get it out of the way. We have this infinitely long line of electric charge. Later on we can scale this down to something finite. But we said make it an infinitely long line. That way whatever point you try to measure at is automatically the midpoint for the system. We'll go ahead and measure the separation distance between that point and the closest point on the line. And previously our author called this Z, but then in this chapter switches over to D. I don't really know why, but I'll stick with the notation that our author is using. And then we need to consider an infinitesimal amount of charge, which we will call dq. And that infinitesimal amount of charge is spread out over an infinitesimal length, dx. And this should look familiar because we used this previously. We called this lambda. This was the linear charge density. And like all other charge distributions, we want uniform charge distribution in this problem as well. So no matter what the ratio, whether it's the infinitesimal sampling or if we're looking at the total charge of the line versus the total length of the line, that ratio has to be the same. Next, let's draw ourselves a right triangle. We will have a distance of r that we measure from the charge to the point in space where we're trying to measure everything. Since we called the the infinitesimal length dx. We'll call the finite length between the midpoint and where the charge is at. We'll call that x, and then up here we had called this theta. So far we should have an identical picture to what we were using back in chapter 22 when we derived the electric field for this system. The major difference is that instead of solving for electric field, we are now solving for electric potential. For an individual point charge, the electric potential produced by an individual charge is 1 over 4 pi epsilon times Q over R. Now we are using an infinitesimal amount of charge, which means that we will produce an infinitesimal amount of the total potential up at our point. At this stage, if we were trying to derive the electric field, you'll remember that we had the evil twin scenario where the electric field lines would come up, the horizontal components would cancel out, only the vertical components would remain, and we would have to incorporate a cosine theta in order to account for that. But those were vectors, and that cosine was put in there to account for the surviving vector components. Electric potential is not a vector, and so we don't have to worry about any components canceling out. Potential is a scalar, and so our evil twins are not going to be fighting against each other. They're actually going to join forces and fully add their electric potential up at this point. Next step, we need to set up our integral, because we need to add up all the potentials that all of these individual charges are going to produce. And our first substitution is going to be 4dq. Right now there's nothing in the expression that tells me how the charge has been distributed in the system, but I can do that if I use lambda. Lambda says the charge is distributed along the line. So we'll go ahead and make that substitution. Lambda dx over r. And now it looks like we're going to be integrating with respect to x. But as I move in and out along that line, not only is x a variable, but so is r. As x becomes larger, r becomes larger, and vice versa. So I need to decide which of the two do I want to use for my variable of integration. And right now it looks like we're going to be using x. I can use x as long as I don't go all the way out to infinity. So now might be a good time to scale down our line. So maybe our line is only a length of L now. So we'll stick with x as long as we can. That means we need to rewrite r in terms of x and preferably no other variables. Well, the only non-variable in this right triangle is d, and that's just going to be Pythagorean theorem. So r squared is x squared d squared, so r, just r, will be root x squared d squared. Looks like we're ready to integrate. So we're going to set up our integral. We'll integrate the left-hand side, and we get v. I'm going to pull all of the constants out to the front. And the only thing that actually needs to be in the integral is the dx and the root x squared d squared. And now we need our limits. So for the limits, we are essentially starting at the midpoint of this line. So we could call that 0. And then we're going to integrate out to the end of the line, which technically is only L over 2 in terms of length. But then everything that happens on the left-hand side is just going to be a duplication. And so we could slap a 2 in front of everything and then integrate from 0 to L over 2. That means that the 2 and the 4 are going to reduce. We get lambda 2 pi epsilon naught 0 to L over 2 dx over root x squared d squared. And we're finally ready to take an integral. Now you look at that and you think back to your days in Calc 1 and you might be saying, well, what kind of method can we use? Usually the default is to try a u/du substitution. But in this case, u/du substitution is not going to work, because the only really valid choice for u would be x squared d squared, and that means that du would have to be 2x dx, and you don't have any extra x terms up in the numerator. You can always fudge the extra constants that you need, but you can't fudge variables, and so u/du substitution will not work for us in this case. So then there's, when you get into like Calc 2, you have integration by parts, there's trig substitution, all manner of even more painful methods of integration. But at this point, you've already passed Calc 1. I'm guessing you're in Calc 2 now, or you've passed Calc 2, but you have earned the right to go ahead and look up what this integral is going to be in an integral table somewhere. In fact, this particular integral is listed in the appendix of our textbook. Our textbook has about maybe 3 dozen different common integrals that are used for derivations all throughout the text. This is one of them, and so what I'm going to do is I'm just going to write out the solution to this integral. The integral itself is going to result in natural log x plus make sure I'm on the right page of my notes here, plus root x squared d squared. Make sure I got that right. Yep. Evaluated at our limits. And then as we evaluate everything and collapse everything down, the final, so we've got some algebra here that needs to be done to collapse down everything, and what we're going to get for the electric potential produced by our line of charge trying to save a little time here. That's why I'm doing this step. We're going to have lambda over 4 pi epsilon naught. So got a 4 back from there. And we have L plus L squared D squared. That's a root term right there. All over D. And that's it. And we are done. Clean that up a little bit. There we go. So, once again, do you have to reproduce the derivation? No. Should you be able to follow along with the derivation? Yes. Should you be able to backtrack a few steps in a derivation to make an appropriate change? And the answer is yes. What do I mean by that? Well, for this particular derivation, we derived the electric potential at the midpoint above the line. What if I asked you to find the electric potential at the very end of the line? Then what would you do? Well, in that case, we would still have changing R values for each individual point. We would still have changing X values for each individual point. We would still have D as the measurement. And so now, really the only thing that we would need to change would be the limits of the integration process. So if we come back to this step right here, we had lambda over 4 pi epsilon integral dx over x squared d squared. And instead of starting at the midpoint and going to L over 2, and then multiplying by 2 to duplicate the left-hand side, we have to start at 0 and go the full length of L. And from there, we would evaluate the same outcome for the integral. We would just have to go back and redo all of the algebraic steps for the limits right there. Alright, so that is the line of charge. That is the potential that we get from the line of charge. Very different from the expression that we had for the electric field from a line of charge. But now we're going to move on to things like, and let's see here, we'll need to look at a ring of charge, a disk of charge, and then we'll start looking at spheres and cylinders. I think we're probably, we're probably getting close to the time where I'm going to have to end the video, otherwise my battery's going to run out. So we'll come back and we'll start discussing what it would take to derive the electric potential for a ring of charge, a disk of charge, spheres and cylinders. And so either one more or two more videos to get through those derivations. But for now, time to go recharge the battery on this thing.